Hello, everybody. Thanks for enduring the day. I will try and get this done as quickly as possible since it's dinner time. This started with a question that was put to me after the last IMC when somebody says to me, "What is it called?" And if we just take a step back and reflect on everything that has happened today and last night, Jeremy used the word taxonomy. And when you think about what we do, it's all about conveying meaning, information, understanding. I've been interested in spectroscopy for as long as I can remember. This is actually a truncated version of what was going to be the original, which was going to take quite a bit longer, but it's been compressed into 10 minutes or so. One of the first books I read was, it's already been talked about, the McKinley's book. And McKinley worked with Millman in the 50s in the International Geophysical year. And at the very early days of spectroscopy, there were only a few hundred spectra that had been secured worldwide over the previous decades. Now, all of the previous, or most of the previous speakers have talked about types, classifications, all the various groupings, because that's part of the process of inferring that understanding. And this was the first system which was used, and it was based on the fragmentary images that were obtained at the time. Little bits and pieces and very, very rare photographs. If you didn't see these lines and you saw those lines, it was a type X. If you didn't see these lines, it was another spectrum, type Y, and so on. So it was a sort of step ladder to a classification scheme. And he also looked at some of the very early velocity measurements, which are now just they're completely outdated. So in 2015, I had been running my video system for about 8 years at this point. It was actually Heary that sent me a copy of this paper because I had contacted him to ask some questions about what I'd been catching. And they produced a sort of catalogue of all the kind of low resolution spectrum they had in their database, and it was an immense amount of work. But they came up with these, I think it's 8 or 9 classifications. And as we've seen from Veronica's talk, this has now gone up to, was it 17? So the detail is becoming more and more and more. The problem is that when you're working with a amateur spectroscopy and you're not dealing with the very, very high resolution spectra, using these very detailed categories is not really appropriate. So what got me thinking, and what my proposal is the exact opposite of Veronica's. I want to take a step back and say, what is the most crude and basic categories that you could use, that if you catch one of these spectra and you want to communicate what it is, how do you describe it? And now, as I said, this was a truncated talk, and there was some history about my photographic efforts. I spent 25 years using film and caught 0 spectra. The first night I blue tacked a grating to my first WATEC camera, I recorded a spectra. But looking at that, up button there, you couldn't really do the analysis that Veronica was talking about. So what can you do? The old classifications don't work, even if you want to look at this straightforward and simple method, which I think is more appropriate to a lot of amateur activity. And also, we're now using mostly silicon detectors, and because of the band gap of the silicon and the physics involved there, the sensitivity bias is different from the older days of the film. So the sort of data set is different anyway. So could it be made simpler? So I went back to my 1300 spectra and started digging through. And actually, quite clearly, it became apparent that yes, you could. And this actually surprised me, because if you take this as broad a view as possible, then you can roll up a lot of the very detailed analysis just into a basic type, so that if you're trying to tell somebody what you've seen, it's just this or that, and it's a starting point for building the more detailed analysis as you go on. So The first one was a type A. I've decided to use the other end of the alphabet rather than the X, Y, Z. These are just the rocky bodies, calcium, magnesium, silicon, sodium, and they are by far the most common. And in my spectra, about 90% of them are of that particular type. And this is the typical WATEC image that I capture. And I chose this in particular to illustrate the point that all of this is atmosphere. These are nitrogen, the oxygen line at 777, nitrogen, oxygen, nitrogen. From the actual meteoroid, all we see is this. But we know from calibrating the system that with the dispersion, this is sodium, that's an iron band, and that's magnesium. So it has some rocky elements, so we would just call that a type A. At the other end of the scale, the sort of standard type A, which this is a sporadic, and this is the issue with the very detailed analysis, is you have a wonderful, beautiful spectrum, but if a single observation, it's not really telling you anything about where it came from or where it's going. So although it's very detailed and you can do the ternary analysis and what have you, it doesn't give you the whole picture about how you can fit into what Veronica was talking about. So it's part of a bigger picture. Another example of what I'm calling a type A is just a stream. That's a quadrantid from 2 years ago. And the quadrantids, I don't know if Peter has got any of these for his book, but the quadrantids are very, very rich in magnesium. Very, very bright green line here. And this is an unresolved triplet, but it's also when you do a relative calibration, this is very, very bright. So again, very detailed. In this case, you would be able to do more detailed analysis, but rocky. We can see the calcium lines, we can see the magnesium lines, we can see silicon. So that's a rocky, so it's still a type A. The next one is a type B, and as Peter also mentioned, these are pure iron, and they are very, very, they're very, very distinct, even at the sort of poor end of the images as well. There's the Hades. They have very distinct groups in the blue, green, sorry, in the blue and in the green. Iron only, nothing else. And again, if you have a nice capture, but it's a single capture, there's no orbital information. So all you can tell is it's a lovely iron spectrum, but we're still calling that's a type B. The other one is quite an unusual one, and Peary actually discusses that in quite great detail because in his analysis, these are a very particular class, but again, in my collection of spectra, they are absolutely distinct. They run to 2 to 3% of all the spectra I've captured, and you can see this very distinct sodium line here and the groups of iron and nothing else. And they tend to be quite low velocity because there's no emission from the atmosphere. So these are traveling quite slowly. They're coming in, but they are very, very distinct. Here's, in fact, one of the advantages of using video as opposed to film is you can run it during moonlight. That's the moon. The meteor fell on this side. Sorry, that side. That's the first order spectrum. Iron lines and sodium. And then this is the second order, the iron lines and the sodium. Very, very, very distinct group of lines. And likewise, another one in my high resolution system. Very detailed, lovely, but no multiple capture. So there's no orbital information with that at all. But the other interesting thing is, in some of the other examples that I have, is this little chap here. That line there is always really very sharp and just a little bit brighter than all the rest. And that's actually apparent in other spectra of this type. So that's it. Of 1,300 spectra, every single one that I've captured, rocky, iron, or the mix of sodium and iron. So if you take a very broad look, you can boil it down to those main categories. And just in case, I've gone back to type X for everything else. Just in case an oddity it comes up. But there are the case where using the dispersion gratings, if the meteor falls in across the grating, the lines are very highly foreshortened, and you just can't devolve them. So you could call that a type X just to say that you've recorded something. And that's the point, is that people who add gratings to their systems tend to do it as a sort of accessory. They have wide field systems, so they produce a lot of low resolution spectra. And it's just having that mechanism where you can say, yes, I've got something to record, rather than just disregarding everything. So as an example of a type X, the spectrum fell outside the field of view, and all you got was the 4 atmospheric bands. So you know there was a meteor there that, you know, produced some lines, but you can't tell anything about it, especially no multiple stations and no compositional information. So that is definitely just a type X. So some quick thoughts. We certainly know much more now than we do, you know, even 20 years ago. The video system has had an incredible effect on our understanding about the composition, because barring having a meteorite, good spectra is as good as we get. It's also got a bit of flexibility that if you do have very strong lines of one or deficient lines of other, you can prefix and suffix just to give a bit more detail. But it's if you have a multiple capture of a very detailed spectrum, then you can do all the proper in-depth analysis, which you would do in any case. The point about this is the simplicity and immediacy, because that's, what do you call it? That's how it started, is that if you have spectra and you start trying to determine the line ratios and the line intensities and all the intensity calibrations, you try to write out longhand, it becomes a paper in itself almost instantly. If you can just have this very basic system where you can use low resolution spectra without having to do all of this, and you want something to log and a mechanism by which to log it, then I think this kind of basic ABC is a good way to start, because you can always build on it and do the more detailed stuff as is required. So having shortened the talk and going through as quickly as I can, because it is nearly dinner time, thank you very much.